Hello friends, you might have seen a big change now the way we are delivering the lecture. I am not moving now too much, and I will be whatever I have to use to write on the board, I will be writing on a pad now, and that will be coming on your screen. Okay, so a slight change from the earlier lectures, okay, but I think it is not going to affect our learning process. So, in the previous lectures we were trying to understand the phase diagrams. Okay. So, now we said or we discussed this, that we are discussing the equilibrium phase diagram. That means the process is so slow and it is reversible, okay, that we can always trace back our step back, and we will be doing the things slowly, okay, so that we allow the system to come into equilibrium at each stage, and that is what we say about the equilibrium phase diagram. However, in the practice the conditions are not under equilibrium conditions, okay, we deviate from this equilibrium condition because we have to do things fast. Our productivity is going to be affected if I do not do the process in with a higher kinetics. Okay. So, today we will like to discuss that in equilibrium condition, if we do a certain transformation, or if I do it in non-equilibrium condition, how it is going to affect the microstructure of the material, okay, because that is ultimately is what decides properties for us, as we have already discussed earlier also, and that we should understand before going any further. Okay. So, today's lecture is on equilibrium and non-equilibrium cooling, and to elucidate the whole process, okay, we will take the simple phase diagram, okay, and one of the simplest phase diagram is isomorphous phase diagram, where we know that both the components are fully miscible in each other. Okay. So, there is no solubility limit. Okay. I can add, for example, copper nickel system, I can add copper in any amount or nickel in any amount without any problem. Okay. So, we will take that system and equilibrium and non-equilibrium cooling we will discuss in that context. Okay. Okay. So, what is the equilibrium condition if we want to do phase transformation under equilibrium condition? Okay, that we have already discussed that we allow or give enough time for redistribution of allowing element, okay, to reach the equilibrium phase composition at the particular temperature. Okay. So, at each temperature you are allowing enough time for phase or for components to redistribute between the two equilibrium phases, so that you reach a equilibrium condition. Okay. So, that is what do we mean under equilibrium condition. Okay. So, one example here, lot of colors on this slide, okay, and this is solidification under equilibrium condition. Okay. And as you can notice that we are using here isomorphous phase diagram. Okay. So, my A is completely soluble in B for all the composition in liquid phase, my A is soluble in B, or B is soluble in A for all the composition in solid phase also. Okay. So, these are called isomorphous phase diagram. Yeah. So, here we will take one alloy with a composition as given here C0 38.6%, okay, and at point 1 we have heated the alloy and we have brought the alloy into completely liquid phase. Okay. So, at point 1 it is completely liquid, and what is the condition of the system at that particular point is depicted in this particular circle here, and okay, we are showing here the liquid as a blue color, okay, and with a composition given by this C0. Okay. So, at this point the liquid phase has composition of 38.6%, okay, and the whole volume is liquid. Okay. And now we started cooling from this condition, okay, and we have come to a condition which is pointed by a number here is 2. Okay. So, at 2 we want to understand that what is the condition of our alloy. So, at 2 as we discussed earlier also, I will draw a tie line. Okay. A tie line is a line which is parallel to the composition axis, or you can say it is a isotherm at a constant temperature, we have that. Okay. And if I want to know that what will be the composition of the solid phase here, the tie line wherever it is cutting the solidus line, okay, that will give the composition of the solid phase, which is given here. Okay. So, see, this is the composition at stage 2 here, which I am showing in brackets. Okay. So, this is the composition of solid at point 2. Similarly, you can see that it is cutting the liquidus line at some point here. Okay. So, I can again plot a line from there, okay, wherever it is cutting here, that will be the composition of liquid at point 2. We can also find out what will be the fractions. Okay. So, this particular arm length divided by the total lever arm, okay, will give you the fraction of solid, and this blue arm length, okay, divided by the total arm length, okay, will give you the fraction of liquid. So, as you can see that this is a bigger arm length. So, I should have more liquid here, and because this solidification has just started, you have just 2-3 nuclei of solid which has formed in the liquid. So, the fraction of liquid is higher, the fraction of solid is lower. Composition of solid is much lower than the overall composition which you took at this stage, okay, and composition of liquid is higher than what we the alloy we have initially designed. Now, after that we have come to the point 3 here. Okay. Now, again I can draw a tie line. Okay. So, the composition of solid at point 3 will be given here. So, I can again write CS in brackets 3. This will be the composition of solid at point 3. Okay. Again I can go and see where this tie line is cutting the liquidus line, that will give me the composition of liquid at point 3. Okay. Again you can see that my solid here still has a lower composition than the liquid. Liquid has a higher composition than the overall composition C naught, and solid has a lower composition than the overall composition C naught. Okay. But since we are doing it at a very slow rate, okay, I am giving enough time. As you can see, the first solid which formed was having much lower concentration of B. The solid at stage 3 which has formed has a composition higher than the what we got at 2. That means, I need now more solute atom from the system to enrich the solid phase here, okay, and to have a equilibrium composition. Okay, I have to give enough time for redistribution of the solute, okay, within the whole solid. Okay. Liquid, again as you can see earlier the liquid composition was very close to the overall composition, but now the liquid composition has increased, okay, because my solute is rejecting the solute, my solid is rejecting the solute in the liquid phase, that is why the composition of liquid is increasing. You can see that I can again find out the fraction here. So, this arm length divided by the total arm length will give me the fraction of solid. This arm length divided by the total will give me the fraction of liquid. So, now liquid and solid are almost of equal fraction, weight fraction. Similarly, at point 4 we can see, again I can find out the composition of solid at point 4, and here the composition liquid at point 4, and again we can find out the fraction. Okay. And when we come to the point, okay, some point here, now the liquid which was getting higher and higher solute content, okay, you can see that slowly the liquid will, the solid will come to this composition, okay, and the last liquid which will form it will give all the solute to the solid, okay, and we have to give enough time to this solid to redistribute the all the alloying elements. Okay. As you can see, if I draw very close to some point here, a tie line like this, okay, you can see that now my composition of solid is approaching the composition of the overall composition C naught, okay, and my liquid is having very high solute content. So, this solute content has to be redistributed in the whole of the solid when it reaches this point at the where the overall composition is cutting the solidus line. Okay. So, all the solute has to be taken into the solid, it has to be redistributed, and ultimately at point 5 I will get a fully solid phase, okay, of these are different orientations. So, you have grain boundary in between. Okay. So, these three were nucleating, they joined together, now they cannot grow, already it is solid, this is solid, this is solid. So, wherever they are joining, you will have some kind of a boundary, okay, and this boundary when we may not be able to call it as grain boundary at this stage, but there is some boundary between the three different grains, okay, and that will be at point 5, and all the solute have now been redistributed according to the composition, overall composition C naught. Okay. So, you can see at different stages the solute had different solute content. Okay. So, equilibrium cooling means we are giving enough time for this solute to redistribute throughout the volume of that particular phase. Okay. So, this is how we do in when we do for under equilibrium condition. Now, we will see what will happen if I am doing it under a non-equilibrium condition. Okay. So, again we have taken a same phase diagram, isomorphous phase diagram, okay, and again I am taking the same 38.6% composition seen of my alloy. Now, I am heating the alloy up to the point 1, okay, and so of course, this will be in liquid state at this point, okay, the whole volume is under liquid condition, okay, and now we started cooling from point 1. So, as soon as it cuts the liquidus line, there will be some solid which started forming. So, we are looking just below the liquidus line at a point 2, okay. Again I can draw a tie line here, and I will show that you have the composition CS here, okay, at point 2, and you have some composition of liquid here which will be very close to the overall composition. This will be Cl at point 2. Okay. Now, these are some solid which has nucleated in the liquid phase, okay. Of course, fraction also you can get. Now, we come to the stage 3 here. Now, you understand that we are doing it at much faster pace. I am not giving enough time for a solute to redistribute. So, what happens because of that? When I go from point 2 to point 3, okay, earlier if you remember, I can show you the previous slide, okay, my the overall composition I depicted with having a same color throughout the solid phase, okay, and same color in the liquid phase, okay. But now, I am showing you that whatever the solid formed at stage 2, it is still having the same composition what it had at point 2, okay, and after that whatever solid has formed over the initial stage, okay, that has a different composition which is shown by an orange color. So, you have a condition here where the solid initially whatever composition it had is still in the same color, okay, and over above that at stage 3 it has a now different color. Of course, because for the discussion purposes we are defining different points here, okay, but in reality it will be a continuous cooling which is going on. So, at each stage you will have composition given by at that stage. So, you can see that I can also divide these stages in multiple, okay. So, between 2 and 3 also you should have gradient of colors here, okay, if you want to show the variation of solute in terms of color, actually it should not be two discrete colors, but it should be a continuous variation in colors. That means it should be a continuous variation in the solute concentration. Okay. So, now you understand that you might have noticed that we are trying to show that you will have different solute concentration at different point. So, at what time the solidification of that particular layer has taken place, okay, you can see it like that it is remembering that this solid was transformed at this stage. Okay, that memory is still there. Okay, you can understand it from that point of view. And liquid also, of course, we are rejecting some solute, so it will be enriched with the solute. That is how we have shown with a different color here. Then I will come to point 4. Now again you can see at point 4 I am showing it with a darker orange color here. Okay, so the composition at stage 2 whatever we had, this is the composition at this stage 3 whatever we had, and this is the composition at stage 4. So, I can write that CS at stage 3, CS at stage 4. Okay, this is liquid at 3 and this is liquid at 4. Okay, so this is how the composition variation is now there, kind of imprinted in the solid. Okay, so now you can also understand that now the solute here is having much lower concentration, okay, then this darker yellow and then the orange one. Okay, so if in the total volume if I see, the solute content must be much lower than what we saw in case of the equilibrium condition. Here the whole volume had the same solute content which is very close to my overall composition, okay, for the whole volume. But in this stage now you have variation. So, if you see the average composition, its concentration in the solid phase, it will be much lower than what is given by the equilibrium phase diagram. Okay, so in this case, in non-equilibrium case, you can understand that the equilibrium phase diagram itself should shift towards the left side in the solid phase. Okay, and now when our whole solidification is ended, you will see that it has a lot of the solute gradient is there in each of the grain. Okay, and that will bring out variation in the solute concentration, and of course the properties will also change, okay, depending upon where you are measuring the a particular property. Okay, so every lot of things changes because of that. So this is the problem with non-equilibrium cooling, okay, which is actually we do in practice. Okay, so you can understand that when we do solidification in alloys, okay, where we have big ingots, okay, the ingots can be size of this room, okay, very long, and then big diameters are there, okay, and that you are doing this solidification. So at different location of this ingot, you will see that there is large variation in the solute content, okay, and that is not a good condition for our material. Okay, so now to get rid of this problem, okay, we have some treatments. Okay, so first let me introduce you to the term which we call as solidification coring. Okay, the solidification coring is that during non-equilibrium cooling, that is fast cooling, the time is not enough for distribution of alloying elements. Since temperature is continuously decreasing, subsequent transformation of liquid to alpha phase takes place with composition which is higher in solute content. This results in segregation of alloying elements. Okay, so you can understand that there will be a large variation in the solute content, okay, or alloying elements, okay, and that is not a good condition. To solve this problem, all cast structures are first subjected to a process called homogenization. Okay. Now, there is always a kind of a solution for any problem. Okay. So, we have a problem here that when you do this solidification at a faster rate, you have problem of what we call as solidification coring. Okay, there will be a difference in the composition at different places. Okay, but there are processes which we can use to bring down this variation, and this is one of the process which we use is called homogenization. So, as the word suggests, it is to homogenize the composition throughout the ingot or throughout the solid structure. Okay. And now if you recollect, one of the process which we can use here is what we understand or what we discuss is in the topic where we talked about diffusion. So, we will take help of diffusion process here, okay, because you can see that there is a large variation in the concentration at different places. So, solid will diffuse from high concentration regions towards the lower concentration regions, okay, and thereby you will have a homogeneous concentration throughout the solid. Okay. So, this homogenization process is basically a diffusion process, okay, where you have this large variation can be brought down by having the homogenization process. So, as we understand, the diffusion process itself is a time and temperature dependent process. So, homogenization should be a process where we take our material in the solid phase itself to a higher temperature. Okay. So, by taking it to higher temperature, one thing is my diffusion becomes faster, okay, my atoms will be ready to move from one place to another place. If it is a substitutional alloying condition or alloy, okay, that means the alloying element occupies a substitutional position. At high temperature, you also have higher equilibrium vacancy concentration. Okay, so that gives you my alloying element to move, it gives additional site for my alloying element to move. So, my diffusion process is faster, I am getting more vacancies to move the alloying element. Okay. So, homogenization is a process which has to be done at high temperature. Okay. Time of course is going to be a factor here for how much time we have to expose. Of course, again in engineering practices, my time is also important, because if I am heating for a material for a certain time, it requires energy. Okay, for that much time my one particular equipment will be occupied. Okay, so both time and temperature have to be played together to get a optimum time for homogenization. So, homogenization is heating of material to high temperatures, of course below solidus in present case, so that diffusion of elements become faster. We know that diffusion will take place from higher concentration to lower concentration. We can give enough time to approach uniform composition within some limit throughout the sample. Okay. So, we do not have to have you can say an ideal homogenized condition where, so that at every place if you measure the solute content, it has to be same. Okay. You have to define a limit that, okay, up to this much variation I can accept the alloy. Okay. Once you have defined that, you will get a reasonable time within which you can do homogenization process to get uniform composition throughout the sample. Okay. So, with that we will stop this lecture here. Thank you.